Okay, I think I'm going to go ahead and get started. I'm recording this anyway, so just in case people come late, they can I can send them a link to the recording. I wanted to recap where we were at. We're still looking at Gauss's law. If you remember what necessitated all this was, we're looking at the E field around different configurations. And a lot of the things were, pretty confusing. Like we know from a point charge, we have a lab that tells us it falls off as the inverse square, the E field does. But then when you start looking at other things like what if it's an infinite line of charge, or what if it's an infinite plane of charge, what would the E field be? It's not as intuitive. We're able to kind of correlate it with the gravitational field. We're able to do that one simulation, or actually that one lab using light, and that kind of backed up what our gut told us. But we need a better method. We need to be able to calculate what the E field is for any kind of configuration. Instead of using Coulomb's law, which kind of can be a pain because you have to worry about all those vectors and everything. And so we started looking at it conceptually. And what we found was that the distance from a charge, as you increase that distance, the E field decreases. But as you increase the distance, the area of, let's say, a sphere around that charge, the area will be increasing because the sphere is getting bigger. But yet the entire time, the total charge inside of that sphere is constant. So, I asked you guys, how could we relate it that the E field goes down while the area goes up and the charge is constant? And you guys suggested that maybe if we do the product of the E field and the area and set that equal to the charge enclosed, and there might be some proportionality constant. Okay, so that's what you guys said. Turned out you guys are absolutely right, and that's called Gauss's law. The key to Gauss's law, though, is this Q here is the Q enclosed. So for part one, we have two charge densities that are on these spheres. And for part one, we're just looking at all the radiuses inside of R1. In other words, look at the blue dotted line I drew. That is inside of R1. Now the question is, how much flux would be through that? What's the net flux through that dotted line? Well, one way to find the net flux is to take the sum of dA. That's equal to the flux. Another way to find the flux is to do Q divided by epsilon naught. That's also the flux. So on the left-hand side, we'd have E times 4 pi r squared. However, on the right-hand side, if you look at the dotted line over here, how much charge is enclosed? Somebody shout it out or type it in. 0. Yes, it's 0. So therefore, the E field has to be 0. And so when we plot this, we just simply have a flat line there. Any questions about that first part? Okay, so we're picking up where we left off then. And today, we're still doing part number 1 here, but now we're doing the next part, where we're looking at R is between R1 and R2. So in other words, let me go ahead and draw another Gaussian surface. We're looking, oops, that's not what I wanted to do. We're looking at a Gaussian surface in this region here with my yellow line. Now before I cut you guys loose, is there any charge inside of that dotted line? We don't care about the charge on the outside. We're only looking at the charge on the inside. Is there charge?
Yes.
Yes, there is. And so we're going to use the same idea, except the Q is not going to be 0 this time. Okay? So I'm going to give you guys about 5 minutes to whiteboard. Do you guys know who's in your whiteboarding groups and everything?
Same as always, right?
Yeah, same as always.
Okay.
So does anybody not know? Okay. I'm going to give you about 5 minutes, then they'll work on your whiteboard. Okay, I'm going to pass it off to Laura and Karina. They're going to present for this next one. Let's see if I can find them. Where are you guys? Okay, I'm going to pass it off to Laura. Can I pass it off to Laura?
Yep.
Okay. Okay, and kind of walk us through how you did this.
Mr. Lampesty?
Yeah.
So are we just want us to explain?
Yeah, kind of explain what you did.
Well, we used like the equation.
For Gauss law?
Yeah, that we always start off with. And then we got to this like E equals Q over R pi R squared epsilon naught. But then you kind of helped us and you told us that Q equals sigma minus the area.
Oh, it's not minus the area, it's times the area.
Times the area. And so that we realized it was like a proportion, like the R1 over the R.
Okay, so we have what, sigma 1, it looks like your final equation is sigma 1 times R1 squared over R squared times epsilon naught. And Eric had a question, I didn't see that. Hold on a second here. Eric, what is sigma again? Sigma is the surface charge density. So it's so many coulombs per square meter. And so when you take coulombs per square meter times the area, which is square meters, then you get coulombs. So, okay. Any questions about our answer here? Okay, then let's go back to, I'm going to go ahead and take the presenter role. Thank you, appreciate it. Okay. Okay, so now we figured out what this is. I'm not going to read, well, maybe I can. Let's see if I can redraw it in here. I believe they had sigma 1 times R1 squared divided by epsilon naught times R squared. Now, I'm going to tell you right now, students get really confused on the R's, and I do too myself sometimes. You got to be really careful. On the summation side, that's where you have your generic R. That always goes to the Gaussian surface. That's some generic R. It's on the other side where you have Q at, that sometimes you end up getting an R1 and R2. It's wherever your surface is at, you know, the charge is at, I should say. So this R1 here, that's really just a constant. That's not changing, but the R is. So I'm hoping somebody could shout out, what kind of relationship is this? Is this a direct relationship? Is this an inverse relationship? What is this?
Inverse squared?
Yeah, inverse square. So it's going to look something like this in between. And I'm not drawing a very good job, but anyway, try to imagine an inverse square in there. Okay. Any questions about this? Okay, I'm hoping you're persisting on this because I know this is pretty difficult. It's going to take a while to get used to these. Let's look at the next section where we're looking at R is greater than R2. So let me draw the Gaussian surface that you're considering now. Now you're looking at a Gaussian surface out here. Before I cut you loose to try this on your own, I want to talk about some of the pitfalls students sometimes make here. You have to be really careful on this one. Is there a charge enclosed? Yes, there is, right? And it's not just, really quickly, oh, wait a second. Jacob asked a question. I want to make sure I get it. Really quick, so why did we use sigma? I'm kind of confused about that. Okay, normally we use Q, right? But it doesn't make sense just to simply have one Q. It's a whole bunch of charge here that's all smeared over the surface. And so we're defining sigma 1 to be equal to the charge Q per unit area of this inner surface here. So maybe I should call A1. And this actually leads me right into the next part here, because when I make my Gaussian surface out here, there's more than one charge. There's going to be a charge on this surface here, so the sigma 1, you have to take sigma 1 times the area, and there's going to be a charge out here, sigma 2, and it has a different area. Okay? Any questions before I cut you loose? You're looking at the summation of both of those charges for Q. Okay, do the best. Have a question? No, no other questions. Do your best. I'm going to give you about 5 minutes to do it. Okay, go ahead and begin. Okay, I'm going to call you guys back, and I'm going to hand it off to Trevor. Again, Trevor's not the only one that has to talk here. Anybody in the group can say something. Okay. Whoops. Whoa. Okay. Shoot. We're not able to see the bottom of your screen though. Oh, okay. Now I think we can see it now. Can you close the chat screen and then on your whiteboard page, close the chat board screen so we can kind of see what you have behind it? Okay, excuse me. So can you explain kind of what the rationale is, basically just for that first statement, and then how you found those Q1 and Q2, and then I think that's fine. I think that's all you have to say.
Well, the first step is basically just what we usually start out with, Gauss's law, with the two separate charges added together. And Q1 is going to be sigma 1 times the area of the Gaussian pillbox that it makes, and then Q2 is going to be sigma 2 times the area of the Gaussian pillbox that it makes.
Okay, and then if you wanted to, you can cancel out the 4 pi, but that's it. I mean, you don't even need to do that. Now, I do have a question for you, and I'm hoping everybody can hear this. Can everybody hear me?
Yeah.
Hopefully.
Yeah.
Okay, now this is important. Think back to when we did Coulomb's law. Did you actually put the sign of the charge in, like positive and negatives and stuff like that?
No.
No, you did not, right? You had to draw a picture and figure out whether they're coming together or if it's repulsive, right? You did not put it in. I want you to look at this Q1 and Q2 here. What if the sigma 1 was positive on the inner surface and sigma 2 was negative on the outer surface, such that the total charge enclosed is 0, right? Can you imagine that? I'm hoping you can.
Yeah.
So in this case, when you're using Gauss's law, will you use the positive and negatives?
Yeah.
Yes, you will. So this one's a little bit different, so you have to be kind of careful about this. When you're thinking Coulomb's law, you don't use those positive and negatives. It's always positive. But Gauss's law, you do have to use the negatives because it looks at the total net charge enclosed. Okay, thank you very much. I'm going to take the presenter role back.
I have a question real quick.
Yes.
Since it just says sigma 1 and sigma 2, we don't know if they're positive or negative. So it doesn't really matter in this case because it doesn't tell us if it's positive or negative.
Right. At this point, we're just looking at the equation. So let me go ahead and modify this a little bit here. I'm going to change my picture slightly. So let's see. We're looking at when R2 is less than R1. Or excuse me, not R1. Okay, it's just less than R. So the way this is being modified is the following. I would just simply put up here a plus sigma 2 R2 squared. And exactly what Laura said, we're not even really caring at this point whether they're both positives, whether they're both negatives, one's positive, one's negative. At this point, we don't know, but that's our answer. Okay, now looking at number 2 down here, though, now we're going to have to graph it. At this point, when we're going to graph it, it does matter which one's positive, which one's negative. Notice for number 2, it says, let's assume that they have the same polarity. So let's say both positive. Okay, so I want to graph this. When I graph this, keep in mind this R1, sigma 2, and R2, and even epsilon naught, those are all constants. So what kind of relationship would this be when I graph it? Just shout it out or type it.
Inverse square.
Yeah, this is inverse square, right? Now the question is that I have for you, will this be a continuation of the other one? So it's, you know, kind of tailing off more like this. What do you guys think about that? No, Jack says no, absolutely not. In fact, my question is it going to be lower, like this,
Higher.
Jack says higher. Let's see if Jack's right. Higher or lower? What do you guys think? Let's ask the whole class. Yes, it would be higher because it's sigma 1 plus sigma 2, and they're both positives. Can somebody explain to me when it might be lower?
If one was negative?
Yes, if one of them's the opposite, yes. Any questions on that?
In order for them to be zero, like the total charge of the thing to be zero, would the charge density for sigma 1 and sigma 2 have to be different?
I think that was Jack in the background. I could just barely hear him, but I think I heard, what if the total charge enclosed, oh, it wasn't Jack, maybe it was Jacob?
It was Ben.
It was Ben. Okay, let's say the total charge enclosed was 0. It was Mary. Let's say the total charge enclosed was 0. So sigma 1 R1 squared is exactly opposite of sigma 2 R2 squared. And in that case, what would happen then is you would have an E field that would be a flat line again. Any questions? Okay, so let's go ahead and go on to the next one. Again, watch the time, 11:45, we're done. Okay, so the next one, choose. I know this is taking a while, but I want to make sure that we're taking our time on this and that every get line, flat line, okay. Okay, the next one in the packet looks like the following. Okay, suppose there is a charge Q at the center. So hopefully you can see that. I have this Q at the center. The cavity, it's at the center of this cavity. The cavity of radius R1 is centered in a non-conducting sphere of radius R0. So this outer shell here is a non-conductor. Said another way, it's an insulator. Those charges can't move. Okay. Assuming the charge Q is distributed uniformly in that shell, determine the electric field as a function of R for R is less than R1. So let me go ahead and draw in the Gaussian pillbox for this. The Gaussian pillbox we're looking at is right here.
Okay, so you couldn't be inside Q because it's a point?
No, yeah, you can't be inside a Q because it's a point object. Okay, so the first part, you're going to figure out what the electric field is inside of that Gaussian I just drew. Any other questions? Okay, go ahead and start working on that then. Any volunteers to present? Okay, Jacob said he could try it. I'm going to go ahead and... Can I pass it? I can't pass it to Jacob, right? I forget. Who else is in Jacob's group? Jack is?
No, it's me, Michael, and St. June. And
Okay,
Michael, I think, is the only one who can take it.
Oh, Michael can. Okay. But Michael can't talk, right? Or can he?
No, he can't.
Okay, so I'm going to wait for Michael to take it, and then somebody else from that group will kind of explain things.
We didn't really show much work. It's just what we thought the final product would be.
Okay.
Obviously, you start with E times dA on the left, and then Q enclosed over epsilon naught. And then we figured since Q enclosed is just a single Q charge, it'd just be the little Q, and then you take the area to the other side with epsilon naught. Makes
sense. Does anybody have questions on that one? Okay, for the whole group, I'm going to go ahead and roll back. Thank you.
Wait, so is that right?
Well, I don't know. What'd everybody else get? Does that make sense?
Makes sense.
Yeah, I think it makes sense to me too. There's only one charge, and yeah, that's what other groups have too. So I think we're going to go consensus. That's what other people have. We're going to say that that's right. There's only one charge enclosed, and that's Q. It doesn't matter what's out here at all. It's only what's inside. And so what they had for this was they had E equals Q divided by 4 pi epsilon naught R squared. And so my question to you guys is, what kind of relationship is that when I graph it? That's an inverse square, right? Okay, so an inverse square, I'm going to go ahead and see if I can kind of graph it. So maybe kind of like this. Okay, so the next part, and I think this is going to be the last thing we're going to have to leave you with. I'm not even sure we'll be able to whiteboard, or we're not going to be able to present it anyway. But what question first? No questions? Okay. This next part where we're looking at is for R between R1 and R0. So let me go ahead and draw in the Gauss surface. We're talking about Gaussian pillbox surface in here. Now be careful with this one when you're looking at Gauss's law, which again is the summation of E dot dA. That part's not hard. I think you guys are starting to see that that's pretty easy. It's not even really something you have to worry about with calculus or anything. But the side that you do need to worry about is the Q enclosed. Q divided by epsilon naught. Okay, my question to you is, what's enclosed in here? How much charge is enclosed? What's one of the things that's enclosed anyway?
The small one?
Yeah, the little Q is enclosed. What else?
Proportion of the big Q.
Eric says half the big Q. Well, the way I drew it, it does look like half the big Q. But realize that this blue dotted line I drew is arbitrary. It could be anywhere inside there. It could be barely in the surface. It could be almost to the end. So there's actually two Qs that are involved here. So this Q right here is actually, yeah, and it's going to be proportional to, let me go ahead and see if I can draw some stuff here. This Q is going to be proportional to, first of all, it's going to be equal to little q. So you guys all figured that out. But it's going to be proportional to the charge that's out here, which is proportional to the volumes. Okay? So do the best you can. Let me tell you one thing, though. It's not going to be 4/3 pi r cubed totally, because there's a hole in the middle. You're going to have to subtract out that hole. So you're going to have a q here times some ratio of the volumes. Volume of the partial to the volume of the whole. Any questions? And you know what? I think we're going to have to hang it up there. So what I'd like you to do is try to do this on your own at home. And then when we get to whiteboarding, we'll be able to continue it the next time we get together. Any questions? Do we have this work? Yes, you should have the worksheet. I emailed it to you, or you can go to My Big Campus on the calendar page, and you can download it from there. Any other questions? Okay. Thanks again for attending, and see you guys later. Bye.
Did you want to